Hello everyone and welcome. In today's video, I'm going to show you how to solve this problem. Let's look at the problem. A weightlifter lifts a 350 Newton set of weight from the ground level to a position over his head, a vertical distance of 2.00 meters. How much work does the weightlifter do, assuming he lifts the weight at a constant speed? So this is a problem on how to calculate work done on an object by a person, such as a weightlifter. So this person went to the gym and then lifted a 350 Newton set of weight from the ground level to a position over his head, which is a vertical distance of about 2.00 meters. And we are to calculate the work done on these set of weight by the weightlifter, assuming he lifts the weight at a constant speed. There are very key information in this problem which we need to take care of. First, we need to pay attention to the fact that the lifting was done at a constant speed. To solve this problem, we first need to determine what are the information given to us in this problem. So we have the data. First, we are told that the weightlifter lifts a 350 Newton set of weight. So the weight is W, which is 350 Newtons. From the ground level to a position over his head, a vertical distance. So we are given the distance, that is the vertical displacement. However, we are given the magnitude as distance, D, is equal to 2.00 meters. How much work does the weightlifter do, assuming he lifts the weight at a constant speed? So we are to calculate the weight, uppercase W, and also speed is constant. So V equals constant, and that means that the acceleration is 0. There is no acceleration or change in speed in the lifting done by this weightlifter. So this means that acceleration is equal to 0 because the net force is going to be 0 on this weight. We can model this weight as a point particle. So we need to draw a free body diagram because we are not given the force with which this weightlifter lifted the weight. We can use Newton's second law of motion to do that. So first, let's specify our coordinate system because it will help us to track the directions of each of the forces acting on this weight. So with our coordinate system, I'll go with the vertical axis because all the forces in this case are vertical. So I'll go with any forces pointing upwards to be positive and any forces pointing downwards to be negative. In the horizontal direction, however, we do not have any motion of the weight in that direction, so we can simply ignore that. So if I represent the weight center of mass as a point particle, we have the weight of these masses pointing downwards, so that is given as W as 350 Newtons, right? And then the weightlifter lifted with some force in the upward vertical direction to lift this weight. So in that case, that applied force is going to be pointing vertically upwards, and that is going to be positive because it is pointing upwards, and let's call that F. So from Newton's second law, we know that the net force acting on this object is 0 because of the condition constant speed or constant velocity, meaning there is no change in the velocity of this weight as the weightlifter lifts this weight over his head. So we have the net force from Newton's second law, that is the sum of all the forces acting on the weight vertically, is equal to ma. However, we are told that since there is constant speed motion, the acceleration is going to be 0. So now we have acceleration equal to 0. So that simplifies the right hand side of the Newton's second law. So we are going to have the net force along the y direction is equal to 0. All right, so now let's look at the net forces acting, or the sum of all the forces acting along the vertical direction on these masses. So one, we just identified that there's going to be the force applied by the weightlifter to lift that weight, and also the weight itself is 350 Newtons. So with that, we can write our Newton's second law as the upward upward force, which is the applied force by the weightlifter, and then minus the downward force, which is the weight of those masses, so the center of mass of the weight, and that is equal to 0 because of the constant speed condition. So we can see clearly that the force applied by this weightlifter is nothing but equal to the weight of those masses he's lifting, and that is equal to plus 350 newtons. So this tells us that the applied force by this weightlifter to lift this weight in a constant speed motion is nothing but equal to the weight itself. However, we are to determine the work done, and the work done is nothing but the force applied on these weights to displace this weight in the direction of the force. So that is the definition for work. When a force applied on an object moves that object through a distance in the direction of the force, then we say work is done. So the general definition for work, as we know, is work done is equal to the force, all right, dot product of the displacement. So in this case, we are using the vertical displacement. That's why we have delta y, which the magnitude of that vector is going to be distance. And then the magnitude of the force is just going to be the numerical value for that force, all right? But we've already established that the force and the displacement both are pointing upwards, so they are going to be positive values. Just as a review, if you have vector A dot vector B, that is equal to the magnitude of A times the magnitude of vector B cosine the angle between them. So this is what we call the dot product of vectors. So with this definition, we can write the definition for work as we have to apply as the work done is equal to the magnitude of the force, so F, the magnitude of the displacement, so D, and then the cosine of the angle between the two. In our case, the displacement is vertically upwards as well as the force applied is upwards, as we just determined from Newton's second law. The angle between them is 0 since they are parallel. Okay, so therefore theta is equal to 0 and cosine of 0 is 1. So cosine of 0 is equal to 1. Therefore, we know that the work done is equal to the magnitude of the applied force, which in this case is equal to the magnitude of the weight times the magnitude of the displacement in the y direction, in the same direction as the direction of the applied force. So now what we can do is we can plug in our values and then find the work. So the magnitude of the force is 350 newtons times the magnitude of the displacement, which is 2.00 meters. In that case, we have the work done to be equal to 700 Newton meter. All right, so Newton meter, we can also write it as joules. The work done is equal to 700 joules. And also the key thing to note here is the difference between the work done on those weights and also the net work done. So here we can see that the net work done is 0 because there's no change in velocity, or there's no change in the speed of the weight as they were lifted. So constant velocity will mean that the work energy theorem wouldn't hold for that, because it says that the net work done is equal to the change in the kinetic energy of the object, right? However, here we can see that the work done is nothing but the change in the gravitational potential energy, right? So if you have the ground here as h equals 0, and then that 2 meter mark here as h equals 2.00 meters, you can see that there's that change in height here is nothing but mg delta h. So mg delta h. So delta h is just the difference between this h initial, that is at the floor level, and then h final over the head of the weight lifter. This brings us to the end of this session. Until then, I'll see you in my next video. Bye bye.